Okay, so we're looking at lesson set 15. And I decided to do it from the last problem to the first, reverse order, because you have to have constant contact with the problems, just a 20 seconds to a minute each day. Talk about the problems, do a problem. That's enough over time as you keep doing that daily. At some point, you really start to see what's happening, what's going on. And a lot of times sequential, I found that students don't have enough time to process what they're looking at. And so I give credit for anybody who processes something correctly sometime before I put a grade on the piece of paper. All right, so we're looking at trig now. We're starting to look at trig. And so the last problem is to graph the sine function. We started with a 3, 4, 5 triangle and looked at the commands, opposite over hypotenuse, adjacent to hypotenuse, opposite over adjacent, and I think the numbers speak for themselves. These are called ratios. And it's very important that you realize that what goes with that command is an angle. And we started conversations about angles can be written in degree measurements or radian measurements. And radian measurements are what we use to model situations, right? Because degrees don't match up with numbers as well as numbers match up with numbers. And that's what I'm going to talk about here in a moment. All right, so radian measurements, what is a radian? I suggest, if you're not sure, look at that video. And as a prerequisite, intro to the unit circle. Very important, I think, topic. A very important video to watch to get a feel for what's going on here. So that it's pretty soon, in another week's time, I'm going to write the cosine of 23 pi over 6. And I want you to be able to answer that quickly and easily, 5 seconds or less. That's the goal by the end of the semester. I give you that, you give me an answer in 5 seconds. And I'm happy to say that if we do it a little bit every day and we make sense out of it, a lot of students can. Okay, so let's look at the unit circle. Let's say that we start measuring angles from here. Let's point that marker over there and let's call that 0 degrees. 0 degrees. And then when the marker goes all the way around, we're at 360. Okay, 0 degrees to 360. We're also looking at the circumference of the circle. And if I make this 1 unit for every size circle, doesn't matter, then the circumference, let's say it's 1 foot. I know it doesn't look like a foot, but let's say it's 1 foot. All right, then I start here at 0. I haven't walked around, but how many feet would it be all the way around? Well, according to this, 6.28. So 0 feet at the start. I go all the way around in that direction. 6.28 feet is how far I would have walked. But we don't use those numbers. We use pi. That's 180 degrees. 0 to 2 pi. 0 to 2 pi once around the circle. Therefore, that's pi over 2. I'd like you to know that's about 1.57 of these radius lengths. Got to talk about what radians are. I've got one of these. Takes me to about 1 radian is about 57.3 degrees. That's a good estimate for 1 radian. And then you go another little bit more than half of 1. If I drew it well, I'd be here. Okay, let me get another circle going. So circle, not too bad for rotator cuff problems. And so the ones that we want to mark right now, pi over 2, that's pi. That's 3 pi over 2, and then back again to 2 pi, once around. Well, what happens if I snip that? Snip it, and I unravel it, and I lay it down just like an x-axis, except I really just laid down the circumference of the circle. And what do we have on the circumference of the circle? We have 0. Let's call this 2 pi. And halfway is about here. That's about half of the way to pi. And that's 3/4 of the way there, 3 pi over 2. Now, if we look at a triangle, put a triangle in the circle. I could put the 3, 4, 5 in here, but would have to have a hypotenuse of 1 if it's a unit circle. So I could have done 1 4/5, 3/5. right? But I really want to work with fractions right now. I really want to just work with heights. And I want to call my angle not A anymore. I'm going to call it X. Remember, what's in the parentheses is an angle. So I'm just going to draw a triangle here. There's my angle. That's 1. Well, if that's 1, then that has to be the sine of the angle. Because I'm dividing by 1. And this has to be the cosine of the angle. And I have a new coordinate based on trigonometry. Cosine X comma sine X. Doesn't here to hurt that right now, to hear that. And if I keep drawing triangles, what's happening? My width's getting smaller. My width's getting smaller. My heights are getting taller. Again, walking around the circumference to that radian measurement. I don't know what that radian measurement is. If that's 1.57, 1.57, one's over here somewhere. Maybe it's 1.34. Your guess is as good as mine. But certainly heading towards the maximum height. This is where height is a max. And I think that's pi over 2. Right, so what did I do? I drew triangles. I watched the heights go in the first 90 degrees up to 1. I think they're going to go down to -1. And I think I'm going to get one trip around the circle, which is referred to as 1 period. Some textbooks say 1 revolution. Go Che. So I'm going to walk around the circle and I'm going to get to 1 at 90 degrees. Well, that's it. I'm boom, boom. And then I'm going to come back down to the midline. Got to make sure everything can be seen. Back to the midline at pi. And then my heights are what? I'm always drawing a perpendicular to the x-axis. Good drawings get good answers. I think my heights are negative. And I think they're going to be at a minimum right at the bottom of the circle. So that's where we're going to be at -1. This is +1, and that happens at pi over 2. -1 occurs at 3 pi over 2. Oops, I missed it. I wasn't looking, but close enough, right? And that's 1 period of this sinusoid. Cosine and sine curves are both called sinusoids. And that's 1 period. Now, how would I do that problem? Because that's been on your tests. Well, I think I'm looking at the equation of a line. Because I think I have to get 1900 to act like pi over 2. It's a max. And I think I got to get 2000 to act like 3 pi over 2 because that's a min. And it looks like I got more than 1 period here. 1 period here, if I'm starting here, 1 period here ends over here. That's 1 period before I start repeating. It's the same distance, what we had before. All right, so I think I have a linear function, and I think we've gotten good at writing linear functions. I don't think it's hard for you anymore. Not only isn't it hard, you're getting it right. So I need 1900 to act like pi over 2, and I need 2000 to act like, well, we got to find out here. That's pi over 2 plus 2 pi. So I think I'm adding 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. 7 pi is 14 pi over 2. So I think I'm at 15 pi over 2. But keep in mind, the important thing is I've changed by 3.5 revolutions. Right? 2 pi is 1 revolution. Fits into that. All right, let's see. 1 revolution, 2, 3.5. 3.5 revolutions. And how long did it take? 100 years. So what's the equation of the line? 1900 gets, x minus 1900 gets us pi over 2. And I've changed by 7 pi. That's my change in y. My change in x is 100. And I'm going to work on a sine function. But I'm not going up and down 1 unit. No. And I'm not, the midline isn't 0. The midline of this one is 45. So I'm going to start my y values at 45. And I know the sine function basically does one thing. It kicks out numbers from 1 to -1. That's its job. And I got to get numbers going up more than 1 because 45 plus 1 does not take me to 50, but 5 does. That's that function. Now, textbooks would use the cosine function. Cosine function has a max over on the right, and I think the brain works better with maxes like heights. So that's why I transitioned to the sine function. But over here, the max occurs at 0, so I don't need pi over 2. It's the same function. I'll write the 0 this time. And where does the sine function get a min? Because, I'm sorry, the cosine function is widths, right? That's the maximum width. That's a max. The min is on this side. And where is that? That's at minus pi. Okay, so let's actually see what happens here. Keep putting this in a bad spot. I'm running out of ink. So the cosine function is 45 plus 5 cosine. And I get the same curve. They're on top of each other, superimposed. So how are the cosine functions and the sine functions different? 90 degrees. If you shift one of the graph 90 degrees, you get the other graph. You go play with the string. All right, so that's a conversation that has started. Obviously, we're going to be trying to get to the point where you can graph easily something like 7 plus 3 sine of x minus 8 over 9. And that's our goal in this class, is to be able to do that easily and understand what we're doing. And we got till the middle of May to do it. Now, somebody didn't cap a marker here. I hate seeing that. That means it's dried out. Bye-bye marker. Let's hope I got another one here because I'm running out of ink. Good, up and running. This problem caused trouble on the last test. I'm sorry that it did. No, it was the first time I actually put a Y here instead of something like a 0. Forgive me, but I think if this was a table like this and I put a 0, you might actually put a 0 there and make a connection. That a graph is a bunch of snapshots. And what snapshot did I give you right now? XY axis, I gave you the snapshot that -9 gets you 0 and that 3 gets you 0. Those are the snapshots that I hope, hey, not right now. Okay. All right. So, lost my train of thought. Student came to the door. This is the 3rd time I've been interrupted. So, that's locked. I'm going through this. And so what else do we have? What else do you see here? I'm hoping you see x squared. You know the shape of the graph of x squared? Yeah, you do. I don't think it's a rocket science to do that. And I've always asked for the y-intercept, which appears to me to be drawn very, yeah, I guess it's okay. It's not the best graph. I should have found the vertex first, right, before I graphed. So let's just do this. Let's get rid of that, because I don't usually draw x, y axes. I know -9 gets me 0. I know 3 gets me 0. Then obviously, whatever is between -9 and 3 cut in half, which appears to be -3. -9 plus 3 is -6. -3 is 6 units from 3, and -3 is 6 units from -9. Well, it would be nice if I could find a y value that goes with -3, but in order to do that, I need a calculation. I got to find a calculation to do that. Oh, there's a calculation up here. Boy, if I put in a certain x value, it tells me the y value. Oh, so this y value is -3 minus 3 times -3 plus 3. Boy, I'm learning how that works. Oh, that's -6 times 6. Looks like it's -36. And we started a conversation. Why is it important to know this? Well, pretty soon we're going to be asking questions like x minus 3 times x plus 9 times 5x minus 3 to the 4th power. When is that greater than or equal to 0? Not only do I want to know the answer to that, but I want to see a graphical representation of that in case you start working with graphs at the calculus level. And these are rate functions. You want to know when you're increasing, when you're accelerating, things like that. Well, you got to have this skill. So let's hope that you pick it up in this class. So those are coming your way real soon. All right, so I handed out a memorization sheet the very first day of class, and I said, you need to know these values. I know people haven't been looking at it because I asked 5√2 on the test. And people were not able to say 5 times 1.41 and do it out. Okay, so they're going to be on the test. And they're on the test because you're going to start working with numbers like this. That's the one that you got to memorize, right? Square root of 3. Right? And I'm not going to tell you now. Well, I have to because other people aren't in this class. So we're using 1.73. We're using this as 0.87. All right. And if I don't see those numbers, then I'm wondering if a calculator came out of a pocket, and that would be a bad thing. All right. So I'm hoping you memorize these numbers. All right. So what do I have? I got the graph right here. I got X values. I got Y values. If you memorize these values, you got the line function, the ln function in your head. Okay. So what doesn't work? 1/3, 1/5. Well, these numbers are getting really small. What happens when I get to 0? It's undefined. So the first thing you want to do with logs is find out how close you can get to all these positive numbers. Because if you don't put a positive number in the parentheses, this calculation doesn't work. Now, why? Because these are the quantities that come from exponential growth. I'll just use a G, and decay. Growth and decay, let's say we at a given time, growth and decay kicks out some kind of amount, an amount that's changing. Right? Well, what's the inverse from time to amount? Amount to times. Okay, just to give it a little context. So your amounts have to be positive, or something isn't growing or decaying. If you don't have something there, can't work with it. So what makes the ln parentheses 0? 0. X equals 0. What kinds? Let's make this a 1. What kinds of numbers are we working with here? A half, a third, a fifth. I got news for you. I can do that forever. I can make numbers like 1/5. All right, that's closer to 0 than 1/3 is. All right, what are the numbers that go with it? Well, the biggest number I have over there is 1.6. So why don't we call this 1.6? Let's go with 1.1. Let's put 1.1. If this is 0, 1.1 is about here. 0.7 is about there, right? And so at 1, we get a 0. Because the ln of 1 is asking the question, what do you put on top of E to get 1? That's the question it's asking, and it's a 0. What gets you 2? Well, if that's 1 unit, I'm going to call that 2 units. And I hope if you have that memorized, you're going to say 0.7. So we'll make that 0.7 right about here. 3. There's 3. What's the ln of 3? 1.1. So that's about maybe 0.7, 1.1, something like that, maybe. I'm starting to see a bend, but I'm always going up. So slowly, almost looks like the inverse of rapid Y values changing, Y values changing slowly. I think I'm doing the inverse of that section of E to the X. And what's happening here? Mirror image, but in the negative direction. 1/2 negative 0.7. 1/3 negative 1.1. 1/5 negative, not a very good drawing, negative 1.6. That's what's going on. And I'm going to standardize our graphs to be a 3-to-1 ratio. All right, we're going to standardize the ln function to be 3-to-1. Maybe I'll do one real quick for you. So there's 1 unit of change right there. There's 3 units of change. I'll put that 3 units of change here. So that's 1-to-3 ratio. And that's how I'm going to graph more difficult ln functions. And you can get plenty of practice speed graphing E to the X and ln of X by going to the playlist and looking at exponential and logs. And somewhere in there should be buried speed graphing E to the X and ln of X. So I'll speed graph. Y equals 3, No, that's the last number I want because I'm working with 3. Let's look at 5. ln x minus 2 over 7 plus 9. Okay, I know my asymptote's x equals 2. That's what makes that. I know I want a 3-to-1 ratio here. 3-to-1 ratio, maybe the numbers are different, but it's going to be 3-to-1 if I pick the right numbers. And I am going to pick the right numbers. I'm going to do x minus 2 over 7, because if I know if I make that 1, I'm going to multiply something times 0. So when is this equal to 1? You want to be able to do that in your head the next time. So I'm going to erase the number 1, multiply by 7 and add 2, 9. So 9 gives me 5 times the ln of 1 plus 9. Oh, okay, that's all right. And you'll find that this section of the calculation always cancels because the ln of 1 is 0. Right? And if I make a 0, I don't have to look at that anymore. I can immediately take that. Okay, and how far is it from 2 to 9? 7 units. So I'm going to make this 21 units because I'm going to do a 3-to-1 every time. So 21 plus 2 is 23. So when does this equal 3? 7 times 3, 21 plus 2, what I already knew, 21 plus 2 gets me 23. Okay, so I put 23 in, I get 3. I know what the ln of 3 is. I'm calling it 1.1. 1.1 times 5 is 5.5 plus 9, 14.5. And the more you do that, the quicker you get. Okay, so now log base 3. This is where I stopped when the last time I got interrupted with a phone call. I was in the middle of talking about this stuff. So what do we see? Well, I know I want 0 for the same reason we just talked about. I know I want 1 for the same reason we talked about, because that immediately gives me undefined, and that gives me my asymptote. And this is how you spell asymptote. I had a young woman in a freshman algebra class, and she said that was an isotope. Okay, very close, very close. Okay, let's move Renee. Come on, Renee. I'm going to pick you up, move you back. There we go. So hopefully I didn't lose you too much on the fact that I didn't carefully look at where the camera was. My apologies. But if I stop the video and start again, oh, it'll be the 4th interruption. So I interrupted myself. I apologize. So I'm going to just do this. It's very similar. Remember, ln is really log base 2.71 x, right? So this is going to be very similar to that. In fact, I'm kind of making it identical in some ways. Kind of, approximating. All right. So what do I want? 0, 1, and with logs, and this is a log, right? We want the base to equal the base in the parentheses. In other words, I'm looking for things like log base 5 of 5, because that's a 1. And I know in a function, when I do the major operation, there's usually some multiplier in front of it, and I like multiplying by 1. And I'm going to pick, well, let's see. I was going to say 15, but that was a major error. I want 125 because that gets me a 3. No, I'm off topic. So in this case, I do want a 3, and I want a 3. All right, so if I pick 0, 0 makes this 0. That's my asymptote. If I pick a 1, I'm going through 0. And if I pick the number 3, I get 1 in this case. Okay, so I don't have that 3-to-1 ratio, but I hope you can see that it was easy to find those 2 points. What's another one over here? Just for the record, 1/3, right? We've been practicing this for a reason. We've been doing those on every test for a reason, so that you can do the calculation. 1/9. Maybe you're beginning to see what's happening down in that section of the graph now. All right, and let's call this h of x. Now I don't have to call it h of x. I can go back to log base 3 of x. So what is the limit as x goes to 0 from the right of log base 3 of x? Well, it's easy to look, put your finger, go to the right, from the right to 0. Heading to 0 from the right. That's what 1/3, 1/9, 1/27 is replicating. I think I'm headed. God, I hope I'm not going down there. I want to go up there. I don't want to go down there. Negative infinity. Stuck in a negative environment forever. Wow, terrible thought. So what's e to the x? Well, you try it. I hope you're pausing the video and thinking about these things before I explain things. You have the table over there. E to the negative 1.6 is approximately 1/5. E to the negative 1.1 is approximately 1/3. E to the negative 0.7 is approximately 1/2. E to the 0 is 1. E to the 0.7 is 2. And E approximations. E to the 1.1, approximately 3. And I'm going to stop there because I'm starting to get rotator cuff problems here. And most of these functions get multiplied by something and added to something. So if you were going to pick numbers here and you had to multiply, what are the easiest ones to use? Well, I hope you're saying 1, 2, and 3. I choose 3 because I think it's easier to multiply 9 times 1.1. It's not really harder than 9 times 0.7. But I don't know. I like 1.1. It's closer to 1. I work with 1 all the time. So what do we got? Just plot those points and you got y equals 0. I hope we can see that, these numbers are heading towards negative infinity and my answers are heading towards 0. So I hope that explains this section of the graph over here. So you got to list your asymptotes. A, b to the x plus c. C is your asymptote. Whether I'm putting bacteria in a petri dish or if I'm putting the pizza in the oven. Doesn't matter. C is the center line, not the center line, but what we are approaching when we go to positive or negative infinity with the x's. One of those is going to give us constant change. Not constant. One of those is going to approach a constant in these situations. So let's just label some of the values. How about we call that? 0 gets me 1. How about we call that one? 0.7 gets me 2. How about we say 1.1, which isn't too much further from 0.7. 1.1, of course, 3. I got to do the same jumps, right? 1.1 gets me 3. And over here, we got negative 0.7 getting 1/2, right? Negative 1.1 1/3, negative 1.1 1/6. Put some arrows on there, and you got a nice graph. All right, so speed graphing e to the x. How would you graph something like y equals 9, e to the x minus 2 over 3. I don't want 2's and 3's. X minus 4 over 5 plus 6. Well, I hope you know that it's positive x, so we're growing. We're going to do some with decay, but right now we're on growth. Y equals 6. And I'm going to let that equal 0. Well, that's quick. A 4 is going to get me 6. If I'm paying attention. And now I'm going to pick, 6 plus 15, right? It's going to get me 6 units of change. God. E to the 0 is 1. 9 plus 6, excuse me. All right. Not thinking about the calculation, thinking about what I want to say. All right, so I'm going to get a jump of 9. And next time I'm going to get a jump of 27 if I pick the right number. If I pick the right number, I want something 3 times that first jump. Something 3 times 1. Okay, so 1.1. So equaling 1.1 gets us 5.5 plus 4, 9.5. Okay, so therefore 9.5 minus 4, 5.5 divided by 5, 1.1. That's 3 times 9, 27, which is what I said, on top of 6. Takes me to 33. Did that right? Yeah. Yeah, I think we're good. But again, trying to get through a lesson set, getting conversation started, take more time, speed graphing e to the x. Look for it. It's somewhere in the channel. Barry probably did it several years ago. And you get rapid fire 5. You get 5 practice problems. And within a couple of days, if you spend a couple of minutes each day for 3 or 4 days in a row, you do it faster than I just did, because I got hung up there for a second. So what's 3 to the x? Well, it's pretty darn close to 2.71 to the x. So we got the same shape, growth. What do we want? We want e to the 0 and e to the 1. I'm sorry, 1.1. That's what I work with. I'm doing I'm doing this one. All right. So we want 3 to the 0 and 3 to the 1. That's what we want. So 3 to the 0 is 1. So if I pick a 0, I get 1, and I'm on top of 0 here, right? The constant isn't written, so it's understood to be 0. And then I'm going to get that 3 to 1 ratio. So I got a nice graph. I'm going to pick 1, and I got 3. All right, so let's keep that in mind. This is what we want. So what happens if I have 5? I'm doing 3, not e. Okay. Then I do x minus 7 over 8 plus 9. Well, what's that going to look like? Well, I'm not 0 anymore. I'm 9. I still have growth, right? And I want this thing to equal 0. Well, that's easy. I see a 7. So that gets me 1. 5 plus 9, 14. I hope you see what repetition did two minutes ago. Allowed me to say that more clearly and quickly. And what happens when I make this thing equal 1? 8 and 7 is 15. I know I'm going to be 3 times that jump. I know I'm going to go up 15 units. 3 times 5. So 3 to the 1, 3 times 5. There's your 15 units, right? Because I'm making this thing. Let's put it in. 15 minus 7, 8 divided by 8. There's your 1. So that's what I'm getting. 5 times 3. That's my second jump on top of 9. Takes me to 24. I'm still talking to you when I do those. If I'm not talking to you, well, I'm concentrating on what I'm doing, and it's smoother, and you get the job done more quickly, and hopefully you understand what you're looking at. Square root numbers. Okay, well, you got to understand something about basic straight, what are the friendly numbers? 0, 0, 1, 1, 4, 2, 9, 3, 16, 4. Now, those are square roots of x. Well, I think my numbers on the left are increasing faster than the numbers on the right. I think my numbers on the left are increasing faster. I'm just picking random numbers, but it takes a bigger number to get a jump of 1. So there's a jump of 1, takes that amount. The next one takes more. The next one takes more. The next one takes more to get a jump of 1. Well, what are you seeing? I'm seeing a start, and I'm seeing slow growth, and I'm seeing a marker running out of ink. Starting to bother me. See if I got another one here. Okay, we're up and running again. Okay, so what do I see? I see negatives are undefined. Square root of -1 is imaginary. We're not going to put it on the XY axis, so I want this to equal 0. So I see it starting at 5, and I get 0 out of the multiplication, and I'm left with a 7. And I pick a random number. Why don't I pick? I like 25. I like making 5s. What makes 25? 30. So let's just randomly pick a spot, and then we can estimate other places. So that gets me 17. And my rise over the square root of run had better equal 2, or I'm teaching the wrong stuff. So what's my rise? 7 to 17, 10 units. Square root of run. The square root of 30 minus 5. Well, you do the math while I look for another marker. Oh, God, that's the one that's dead. Let's see. Almost done. Okay, another marker here. Got to start getting some refills. Now, what would happen? I'll just do one more here because this is some of the stuff we're struggling with. So you can try x plus 6 plus 8. All right, you try that one. Pause the video and try it. I'll just look at it, graph it quickly with the way I did the other one, minus 6, 8. I'm looking at 19. Gets me minus 15 plus 8, minus 7. Might have made a mistake there, but that's what I think it is. So we got another 3 or 4 graphs, and we're starting to head to the easier ones that you've had more practice with. All right, let's see if I can get one more marker to get me through this. Okay, we're going to the blue. All right, so weeks ago, we looked at y equals x. We slapped an absolute value on it, and we found that we got a sign change. And we got a graph that had a V shape, two linear components. I see a positive absolute value. I know I have that shape. Absolute value measures distance. What's the smallest distance you can travel? You're going to take a vacation. What's the smallest distance you can travel? Your trip gets canceled because of snow and you don't go anywhere. So that is a minimum. This is a minimum for an A value greater than 0. And this is an A value. So I hope you can see 3, 4. And I've been asking for the y-intercept because folks put it on the wrong side of the graph often. And I hope you know 0 is an x value. And that's an x value. And I hope you know 0 is to the left of 3. And if I plug 0 in, I can see I get 10 out, which tells me immediately that 6 gets me 10 as well. And it's graphed. 2x squared minus 12x plus 7. When I see this, these are the steps I take. Let's see if I can move this closer. Hope I'm writing more clearly today. I see a quadratic cut shape up. I know I'm on the decreasing side. My y-intercept is given, so I know that's 0, 7, which means my x is positive. So I just divide 12 by 2, 6, and cut it in half, 3. That's what I do. And then I plug 3 in, and I get minus 18 plus 7, minus 11. I think I'm done. And then I put a 6 in. That also gets me 7. And then I know my roots. Roots are 3 plus or minus. How far do I have to go to get to 0? Minus 11 to 0 is 11 units. And I'm multiplying by 2. So those are the roots. Now, you got to take more time, right? Because you haven't been doing this for as long as I have. So where do you start? Well, I hope you start here. I hope you get through this with some kind of marker that works. I hope minus b over 2a, which is buried in the quadratic formula. Minus the opposite of minus 12 is 12 divided by 4. Well, there's our 3. And I hope you know that that's the y-intercept, so that immediately puts you here. So what do you have to do? Got to plug 3 in. I took a shortcut. 3 squared 9, 18 minus 36 plus 7. I've seen that so many times. I know it's the opposite of this number, or cut that in half. And that's how I got minus 11. So I did that problem. 2 more. And the last one I'm going to talk about a little bit in the context of where we're going to go with it. I got a good marker now. Not to belabor the point, but one of the test questions everybody's getting right, let's move the minus 2 to the other side, put it in the form that I like. Minus 5 gets you 2. Change by 4. Change by 3. Plot those locations. Negative 5, 2, estimate. Negative 5, 2. Change by 4. That's about 4. Go down 3. Make some arrows. It's not a line segment. This goes forever. This coordinate here, does it look like minus 1, 1? You check. Yes, we're done. I'm starting to see everybody get that right. 3x minus 5y equals 0 equals 30. 3 times x is a product. We always set products to 0. And if you plug 0 in, not hard to see that as negative 6. You plug 0 in, it's not hard to see that as 10. And if I don't see these two numbers, and I'm not seeing it from everyone, you're missing the conversation somewhere. Okay, so standard form, if I give you a standard form, I want you to use it. 0, negative 6, 10, 0. And make the connection that a subtraction here gave us an increasing function. Now, what are the other things I'm going to say? We're going to build off this concept, and we have been slowly. You may not realize it, but I've been asking you questions like, name x minus 5 squared plus y plus 3 squared equals 49. I've been asking for coordinates. It's not any different than that. I've got a calculation adding up to 49. If I can make one of them 0, I think I can make that 0 by putting a 5 in. Then I think I can see 4. And with a little extra work, I think I can see -7. And if I made that 0, then everything's got to come from this. I can see 12 and I can see -2. And if you plot those, you'll find out that you're at a center 5, -3, and you got a radius here of 7 units, getting us to those 4 locations. 5, 4, 5, -7. 5, 4, 5, -7. How far is it from -3 to 4? 7 units. And so we've been working with the center of a circle and a radius. Okay, what happens if I divide everything by 49? What do you get for a graph? You're going to get the same graph. Okay, I'm doing a video. I'm almost done. Okay, I'll be out in 60 seconds. Okay, good. That's the 4th time I almost had to stop, but I won't. That's all right. Be gone in a minute. All right, almost happened again. I'm going to put a do not disturb sign on the door. All right, so where are we going next? Oh, what if that's 25? Now it's not the same equation. Well, it turns out it's close. We're going to start looking at ellipses, where we're going to move 7 horizontally, but we're going to work vertically 5 and 5. Maybe you can see where those numbers come from. And if I know the center, is 5, -3. It's not hard to move 7 units to the right. 12, comma, -3 is on the graph. 12, comma, -3 is on the graph. True. Yeah, so we're building off of these problems. It's not just this lesson set isn't just you're working with one problem, move on. You're going to use one problem to build into the others. And that's what we're doing now. And we're hopefully at a point where the last test scores were much improved. And so I feel like we're starting to accelerate now in our learning, because I think you're probably figuring out you can do this. And with the practice, not only can you do it, but maybe understand what you're looking at. That's the goal. All right. So I will do the other 40 problems or whatever, 40, I don't know how many, but I'll get to it later today with a sign on the door. All right. Ciao.